Hello, fans of math analysis, pre-calculus, and the general liberation of algebra. We're going to talk a little bit about sequences and series today. What is a sequence? A sequence is an ordered progression of numbers, and that could come in so many different flavors. It could be a simple progression like our counting numbers, 1, 2, 3, 4, dot, 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 forever, right? Those are just going up by 1 each time. It could go 2, 4, 6, 8. That would be going up by 2 each time. It could go 2, 4, 8, 16. So now we're talking about a doubling sequence, something that's doubling from term to term. It could be 1, 4, 9, 16, the perfect squares. You could think of those as the integers consecutively squared, or as adding the next consecutive odd number each time. But as you can see, there are many different flavors of sequences. You could really classify all of them into two primary types. They're either going to be finite or infinite. Finite meaning that we're going to come to an end with our sequence, and infinite, of course, meaning we never will. You're going to see a lot of infinite types in calculus next year. Right now, we're going to focus on a couple finite types, and to be more specific, we're going to do arithmetic and geometric sequences. Once again, this is in your notes. Finite sequences end, they have a last term. Infinite sequences do not. Here's a couple examples of these sequences. Here's a sequence that has exactly 5 terms. It has a last term, so it's increasing by 5 each time. That would be a finite sequence. Here's a couple that go on and on. There's that doubling sequence we discussed. And here is just a generic sequence of terms, A1, A2, A3. But you can see by the ellipses at the end that those sequences are not going to stop anytime soon. Let's talk about those arithmetic sequences. They can be written in the form A plus D, A plus 2D. What does that mean? What are we talking about right in here? Well, first we add 1D, and we add 2Ds. It looks like we're adding an extra D each time. That is, they're increasing by the same amount each time. That should sound familiar because that's one of the first functions you ever studied back in Algebra 1. We called them linear sequences, and that's pretty much exactly what we're talking about. We call that difference between the terms the common difference. And in this notation, it's signified by D. And here are some examples. So example 1 here, we have a arithmetic sequence that starts at -6 and then climbs to -2, +2, +6. What's happening? Oh, it's increasing by 4 each time. The common difference would be 4. Next, we have an arithmetic sequence. It starts at -7 and then goes to 4. That is an increase of 11. Does it increase 11 again from 4 to 15? Sure it does. So that's how you can identify an arithmetic sequence fairly quickly. It's just a linear sequence that increases by the same amount each time. The other kind of sequence we're going to be looking at closely are geometric sequences, and those are the type we looked at kind of like example 2 up here, which had a multiplication to get from term to term, the same number. We call that R, the common ratio. Here are a couple of examples. Example 1, starting at 3, then moving to 6, which means it doubled. Well, if I double 6, I get 12. Once again, double. And so this has a common ratio, of course, of 2. This other one's a little weirder, -2, 2, -2, 2. It's not really rowing or shrinking. It's really just flipping back and forth between positive and negative. So all that's happening is we're multiplying by an extra -1 each time. And we'll talk about that more in just a second. But let's first learn how to write an arithmetic general formula. This will be important for you to do. Luckily, it's something that you got a lot of practice with back in your Algebra 1 days. This is kind of, I think, the quickest method of doing this. You look at that first term and you say, oh, it increases by 4, up 4, so that's plus 4. Hey, 4n, boom. You know, you're used to writing 4x for slope, but since they're using n's for our counters here, we're going to use n. And then we have to do a little test, because I'm pretty sure that for that first term, 4 times 1 is not equal to -6. 4 times 1, of course, is 4. So the question becomes, how do I get from 4 back to -6? And the answer is to subtract 10. And once you have that general form, it's very easy to say, find the 10th term, as it's asking us to do right here. What is the 10th term? We'll just plug 10 in to our formula, and 40 minus 10 is equal to 30. Now, there is a fancier way of doing this. This is a form that will work every single time. The first term plus n minus 1 times the common difference. And let's check that out. The first term is -6, so I'll start with a -6 plus n minus 1, and then times the common difference of 4. It looks a little bit uglier, but if we distribute that 4 and then combine the -6 and the -4, look at that. It's the same exact thing. Now, I don't mind if you use it that way. I mean, that's totally personal preference, but I will tell you, I think that it's much quicker just to do it the old Algebra 1 way. The geometric sequence is probably a formula you'll want to pay more attention to. These aren't as intuitive, and you haven't had as much practice with them. But the formula is pretty easy. You take the first term, a1, and you multiply it by the common ratio, whatever it is, raised to the n minus 1 power. Let's test it out on our examples here. The first example was doubling each time, so the common ratio was 2. So 2 is what's going to be raised to the n minus 1. But the first term, remember, that was a 3. And it's really important that you get that in there, especially when it's not a multiple of the common ratio. Sometimes if it was a multiple of the common ratio, like a 4, you could kind of combine them and massage the exponent a little bit and make it still work out. But it's much safer, I think, just to follow that formula. And then that makes it much easier to use your formula to find deeper terms in the sequence. For example, a to the 20 would just be 3 times 2 to the 20 minus 1, or 3 times 2 to the 19th. That's a big number, so these would definitely be calculator type problems on any of your assessments. The second one, like as I mentioned, a little bit weirder. Let's still follow the rule exactly. So a1 is the first term, so we're actually going to throw a -2 there. And the common ratio is -1, so we're going to throw the -1 being raised to the n minus 1. Now, the whole purpose of that -1 is just to turn our sequence back and forth from positive to negative like a light switch. If you test it for that first term, 1 minus 1 is a 0. Anything, even a negative number raised to the 0, becomes a 1. And so you just get -2 times 1, and that's why we start with a -2. But then from that point on, we're going to be multiplying a negative times a negative, and then a negative times a positive, and it'll switch us back from negative to positive right down the road. You could use our formula to figure this one out, but I think that once you know that all the odd terms will be negative and all the even terms will be positive, we know the 20th term would have to be positive. And that's about it for sequences. Maybe we should talk about series now. Series are very closely related to sequences. Series are what you get when you take your sequence and add them all together. The sum of the terms of a sequence are called a series, and just like we had the two primary types of sequences, we have finite series and infinite series. The infinite series can get very interesting. In calculus, you'll talk about testing whether these series are going to diverge, meaning they're just going to keep adding up into infinitely large sums, or whether they're going to converge. And if the limit of your terms, as you get larger and larger, starts to tend towards zero, you can count on them actually converging. And if they don't, like in this rule right here, then they're going to diverge. Guess what? Good news, you don't have to learn about it yet. But here's a couple examples just to have something to look forward to for next year. Here's a really simple series where we just have the counting numbers. So we'll put a 1 in and then a 2 in. But we're going to go infinitely with these sums. And what you'll get when you do 1, 1 plus 2, 1 plus 2 plus 3, is you'll get these numbers that look like this. If they look familiar, they're called the triangular numbers. You may have learned about them in geometry, but they're not going to get any smaller. They're only going to get larger and larger and larger, tending towards infinity. We call this diverging, moving away from everything, moving towards infinity. That's a diverging series. This really scary looking one right here actually turns into quite a pretty pattern. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial. This is actually, believe it or not, an example of a converging series, because if you continue to add these together, what you'll find is they create the sign of x, given an angle in radians. This is a little beautiful thing that Sir Isaac Newton came up with when he wasn't too busy dealing with gravity. So you'll get to play around with this stuff in calculus, specifically Calc 2 in college, or probably Calc BC in high school. So here are those two series that we were looking at. We're looking at finite arithmetic series or sequences, and the sum of a finite geometric sequence, so the finite geometric series. These are the two that we're really going to focus in on. This first one has a very nice, fairly simple formula, n times a1 plus an. What does that mean? A1 is the first term, an is the last term. We add the first term to the last term. Remember, there will be a last term because we're only doing finite series, and then we divide by 2. The sum of a finite geometric series is going to be a little bit of a weirder formula. This series right here, this formula right here, I can show you where that comes from. Mostly comes from a little formula that a guy named Gauss came up with, one of the most famous mathematicians of all time. So famous, he's often called the Prince of Mathematics. And he was really smart even as a youngster. In fact, when he was in grade school, he used to be so fast with his work that he would often drive his teachers a little bit crazy. And the story goes that one day, just to keep him occupied for a while, his teacher said, Frederick, why don't you go and add the first 100 numbers, and when you're done, you come back and tell me. And Gauss went back to his desk and he started writing the numbers, and he's like, this doesn't look too interesting. Perhaps I should look at them in a different way. Maybe I should look at them backwards, right? And he didn't really see anything specifically about that line that was interesting, but then when he started adding 1 plus 100, 2 plus 99, 3 plus 98, etc., he found that they would always make the same sum. And once you have the same number being added, you no longer have to use addition. You can now use multiplication. He said, I have a bunch of 101s. How many 101s do I have? Oh, I have 100 of those. Oh, but wait a second. I've added these together twice, so I probably need to make an adjustment on that. And so basically he added the first and the last term, right? Added the first and the last term. Figured out how many of those terms he had, which was 100, and then divided by 2 because he was adding them together twice. So if you take that into context, the number of terms multiplied by the sum of the first and last term divided by 2. And that is exactly your formula that you have right here. So that's where that one comes from. The geometric formula is a little bit trickier, but let's take a look at it. First of all, we need to be able to determine the common ratio, and we have to be able to determine the number of terms. So in this case, A1 is the first term, and we're going to multiply that by 1, subtract the common ratio raised to the number of terms in the series divided by 1 minus just the common ratio. Now, don't get yourself in trouble thinking that you can cancel any of these r's or those 1s. You cannot cancel across addition or subtraction, so please be careful that you simplify those very carefully on your calculators when it comes time to do that. We should probably start looking at some examples here and see how we're doing. So I'll tell you, this first one you could certainly do with a calculator or in your head, probably in a matter of seconds, but let's pretend it was a little bit trickier. The really important thing you're always going to need to write for these is the formula for a couple reasons. It looks like the common sum on this is 3. It's going up by 3 each time, but 3 times 1 is not equal to 4, so I better add 1 to that. That is my formula, 3n plus 1. So now I can do my sum. Notice that the formula always wants us to start at 1. People often ask, do I have to start at 1? And the answer is no. You can start at 0, you can start at 2, but then you have to adjust your formula to account for that. And I'll be real honest with you, I see more people who can't make that proper adjustment than who can. So my suggestion is simply to use the formula as it's given in the book. That's the safest way of doing it. So let's start at 1. And in this case, we know there are 6 exactly terms. If we didn't, though, here's what we could do. We could say, well, 3n plus 1 is my formula. And my last term is 19. So if I solve this, it will tell me how many terms 19 is out from the beginning. So that would involve what? Subtracting 1 from each side, dividing by 3. And of course, we already knew there were 6 terms just by glancing at it. But this trick is going to be very important for you moving forward. So we're adding up the first 6 terms of this sequence right here, and this is something that we are going to ask you to write as part of your work before you use the sum formula. So please get used to practicing writing that summation statement, but then you just go right into using the formula. The formula is the number of terms, which we know is 6, multiplied by the first term, which is 4, plus the last term, which is 19, divided by 2. And could simplify this a little bit. 2 goes into 6 3 times. So we're really just doing 3 times 4 plus 19 is 23. So 3 times 23 is what we're doing. 3 times 23 is 60. And I know that this stylus is not writing very smoothly. I certainly apologize for that. I will try to get a better stylus for you. But there you go. There's your answer. You can see that the arithmetic series are really not that bad. Let's do it on this one. Now this one's gonna be a little trickier because, as you notice, the 55th term is not as easy to determine. You can't just count out and say, oh, that's the 6th term, that's the 8th term. We don't know. So I think the first thing we better do is come up with our general formula. It looks like this term is going up by 4 each time. From -5 to -1, -1 to 3, the increase is 4. So let's call it 4n. But 4 times 1 is certainly not -5. I think I would need to move backwards 9 units to get back to -5. So there's our formula. Okay. Now, if I want to know how far out it's going to be to get to 55, I'm going to have to solve this little equation. 4n equals 55 plus 9, right? 64. So it looks like we are 16 terms into this particular sequence that we're going to need to add up. So let's go ahead and write our summation statement. We're going to be adding from term 1 to term 16 of 4n minus 9. And that is going to be 16 term multiplied by the first term. Oops. Make an adjustment. I was going back to first series. Sorry about that. And so -5 is what we were looking for there, right? Whoa. Now I've got the wrong pen, right? I better try that one more time. I'll just do it this way. -5. The last term looks like it's 55. And we're going to divide that by 2. So what do we end up with here? We're going to end up with 16 times 50 divided by 2, which you could either look at as 16 times 25, or you could cancel the 2 and the 16 and look at it as 8 times 50. Either way, you're going to end up with, it looks like a cool even 400. And there you go. You've now summed the second series. Let us see what we got going on with this last example, example C. It's always going to throw some people off when we start seeing fractions. I get it. But you're always going to be in a better place if you can see them with a common denominator. The only denominator we see right now is 2, so that actually makes it a little bit easier. But I would definitely write these out, these whole numbers out, in terms of halves. And I think that it won't take very long before you realize what's happening. Oh, look at that. I'm adding 5 halves, boom, 5 halves, boom, and that is our common difference, 5 halves. So our formula is going to be 5 halves, n or I or j, whatever counter you prefer to use there. 5 halves times 1 is, of course, 5 halves. How do we get from 5 halves back to 1 half? Well, we'd have to subtract 4 halves, or 2, right? So there's our formula. So let's write our summation statement. Sum, starting at n equals 1. And we're going to be doing 5 halves n minus 2. Now remember, for our formula, we're going to need to know how many of these terms there are. And this is usually the one part of this that requires a little bit more work. What is that n going to be here? So let's go back and set our formula equal to the very last term, which is 31 halves. 31 over 2, right? And then solve it. So 5 halves n. Now I'm going to have to add 2 to each side here. Now remember, 2 is 4 halves, so I'm going to end up with 35 halves. And then you could use the old algebra 2 trick of multiplying by the reciprocals. And the 2's would cancel, and we would get, it looks like, 7. So it looks like we are 7 terms out for this particular sequence, which finishes my summation statement and then allows me to write the sum. The sum is going to be the number of terms, 7, added to, or multiplied by, I should say, the sum of the first term, which is 1 half, and the last term, which is 31 halves. And don't forget to divide that by 2. So what are we going to get here? 7 times 1 half plus 31 halves is 32 halves, which I think we probably could just call 16. And 16 divided by 2 is 8, and 7 times 8 is 56. So there you go. Arithmetic sequences, pretty simple to find the formulas, pretty simple to write. Let's do some geometrics. They tend to be a little more challenging for most people. The first term looks like it's just a term that multiplies by 5 each time. The first example, A, 1, 5, 25. So I think the formula is going to be pretty straightforward if we stick with the formula that we saw back on the previous page. In fact, you know what? Let's go back and grab that and take it with us as we go, all right? So we're going to grab this formula right here and take it along for the ride. All right. Oops, wrong one. This is the one that we definitely want to get used to using right here. Okay, know this formula, get used to it. It will be your friend, okay? So it's going to be the first term, which is 1, multiplied by the common ratio, which is 5 raised to the n minus 1 power. Now, we don't really need the 1 in this case, so really you could just write it as 5 to the n minus 1. Seems a little weird not to have that 1 in there, but remember that when that first term goes in, 1 minus 1 becomes a 0, and anything raised to the 0 gives us the 1 we needed to start with. So we're gonna have the sum starting at 1 of 5 to the n minus 1. The only question is, how many terms are there? What is 15,625? Is it the 5th term? Is it the 10th term? Is it the 20th term? That's usually the most work with these problems. So here's what we're going to do. We're going to set up an equation where we have 5 to the n minus 1 is equal to 15,625. Sometimes you're going to have to do a little subtraction or division before you start one of these. If you have that first term it's not a 1. But in this case, we don't need to do that. we can go straight to the way that we solve exponential equations, which is converting them into logarithmic equations. Now, maybe you happen to just know, your first 10 or 15 powers of 5, and you can convert 15,625 directly into a 5 to the x. But most of us don't. So what we would do is we would say this is going to be log base 5, right? 5 is the base of 15,625 is equal to n minus 1. So now we just have to figure out what log base 5 of 15,625 is. Different ways of doing that, right? Probably your favorite way would be to go to your logarithm function, type in the base you want, which is 5, and then type in the 15,625, and just hit enter. And the answer is 6. Boy, that was easy. Unfortunately, as you know, sometimes your log function will be locked up, and you'll have to use something like a change of base formula. So please remember your change of base formulas. They're pretty easy if you just keep them in the back of your mind. If your calculator is in press test mode, you'll only have natural log and log available. So in this case, we would do the natural log of the original argument divided by the natural log of the original base. That's all you need to do. Look at that. You get the exact same answer. Okay? So I'd love to tell you that we're completely done now. Some people do stop one step too early, but remember, we've only solved for n minus 1. We need to add 1 to really, truly finish off the process. So we're 7 terms out, and now that we know that, we can go and finish this problem, okay? The formula for the sum, which is this guy right here, says to take the first term, which is a 1, and multiply it by 1 minus the common ratio, which is 5, to the, and this is where we needed that 7, to the 7th power over 1 minus 5. The 1 out front is really irrelevant in this case. So really, we just have what's going to be 1 minus 5 to the 7th divided by negative 4. If I was you, I would just plug that into your calculator just like that. 1 minus 5 to the 7th divided by negative 4. And there's your answer. 19,531 is the sum of the first 7 of these powers of 5. Now, some of you are, pretty good about exploring the dimensions of your calculator, and you have discovered that there is a wonderful little template called the Summation Template. Look at that right there. Middle row, about 6 or 7 selections over, right? And it allows you to pick your, you might as well just use x here, from 1 to 7. What was our formula? Wasn't it just 5 to the x minus 1? Isn't that amazing? Wasn't that simple? And of course it is. And I would totally encourage you to use this to kind of check your work as you're doing your homework and your practice problems. But please realize that just as the base, the open base logarithm template is locked up in press to test, your summation templates are also locked up in press to test. So you really do need to know your formulas for the sum of geometric and arithmetic sequences. All right, this next one looks a little bit intimidating, but they actually give you pretty much the basis of the formula right here. It's kind of included in the process. Now, if we look, what happens from 32 to 4, it looks like we divided by 8. And if I divide 4 by 8, I get 1/2. And if I divide by 1/2 by 8, I get 1/16. So we're definitely, dividing by 8 or multiplying by 1/8. So 1/8 is the common ratio. But the nice thing is they pretty much give me the formula. Look at that. They give me the first term, 32, multiplied by the common ratio and raised to the 5th power. So not only are they giving me the formula, but they're pretty much giving me how many terms out we're going to be as well. The formula being the first term, 32, times the common ratio, 1/8. To the n minus 1. And if I set this equal to 32 times 1/8 to the 5th, we can see that 5 has to be equal to n minus 1. If n minus 1 has to be equal to 5 for that last term, that means we're actually going 6 terms out to get this relationship. So with that being said, we can set up our summation statement and our sum formula. So here we go. We've got starting from 1 and going to 6, 32 times 1/8 raised to the n minus 1. And that's going to be equal to, as our formula tells us, the first term, which is 32, multiplied by 1 minus the common ratio, 1/8, raised to the nth power. So that's why we need that 6 right there, right? Over 1 minus 1/8. So despite what Mr. Moore has told you about fractions being your friends, we know that fractions always make things a little bit more of a pain. This is going to be 32 times whatever, 1 minus 1/8 to the 6th power is. I'm sure it's going to be a really fun number, so I think we should just use our calculators to put that in. Now the bottom is just going to be 1 minus 1/8 is actually just 7/8, right? So 7/8. So that part of it's really not too bad, but this is where I think we would use our calculators and just let them determine the nitty-gritty of this calculation. So 32 multiplied by, let's go ahead and bring parentheses in, fraction bar, 1, subtract, and I'm going to go ahead and do, I just like to be careful, so I'm going to use parentheses again, 1 divided by 8 raised to the 6th power. And down below, you could either write 1 minus 1/8, or because we know 1 minus 1/8 is 7/8, you could just write 7/8. But when we hit enter, it'll give us the answer. Now, this is in an exact fractional form, so that would be fine. But you could certainly also get a 3 decimal approximation by using your approximation button. So 36.571 is our approximate value. All right, one last problem. Let's give it a quick look. This one is also a little bit interesting because it happens to be an alternating series, meaning it's switching back and forth from positive to negative terms. How do I get from 6 to 30 times -5, right? How do I get from -30 to positive 150? Well, it better be times -5 again, or it's not a geometric relationship, and it is. So our formula is going to be the first term multiplied by the common ratio, which remember is a negative 5, and then raised to the n minus 1. And that's, once again, in your page of notes. I'll go ahead and pull this one over one more time. This is such an important formula for you to remember. The formula for a geometric pattern. Now, how many terms out am I going to be? Well, I guess we're going to have to set this equal to negative 18,750 to make that determination. So this is one of those examples where we're going to need to divide first by 6 before we can start looking at turning it into a logarithmic relationship. So negative 5 raised to the n minus 1 is equal to negative 18,750 divided by 6. Negative 3125. All right. So here's where things get a little weird. If I convert this into a logarithmic relationship right now, log base negative 5, well, we can't have negative bases in our logarithms. We also can't have negative arguments in our logarithms. And you can see that this whole thing has just blown up. So here is the trick. If I didn't have the alternating aspect of this, if these negatives here and here, if those negatives weren't there at all, it would not change the fact that I was just multiplying by a regular 5. The absolute value of these numbers would not change. So basically what I'm saying is that 18,750 would be the same number of terms out if everything in this thing was just a positive number. So that's what we're going to do. We're going to pretend for a short amount of time here that we just have positive values. And it really is just a quick little adjustment. And then from there, you go back and you start using the original formula again. So I'm going to do log base not negative 5. I'm just going to do log base 5. I'm not going to do negative 3,125. I'm just going to do 3,125. I'm going to set that equal to n minus 1. Maybe you get used to change of base right away. Maybe you know that you're not going to be able to use your function, so we start practicing on our homework, and we do natural log 3125 divided by natural log 5 is equal to n minus 1. Or if we add 1 to each side, right? Natural log of 3125 divided by natural log of 5 plus 1 gives us how many terms out we are. So let's go and figure that one out. Natural log of 3125 divided by natural log of 5 plus 1. Don't forget to add 1, preferably not in the fraction, but after the fraction. Because if you do, you'll be 1 off on your formula and your summation expression. So 6. We're only 6 terms out. That's not too bad. And so now we can finish this problem. Summation statement is going to be the sum from n equals 1 to 6 of, this is where we got to remember to bring that negative 5 back in, negative 5 to the n minus 1 times 6. I actually kind of like to write my 6 out front, so I'm gonna try to squeeze it in there. Sorry about that. And we know that it's equal to the first term, which is 6, multiplied by 1 minus, and then you really got to be careful about using parentheses here. Your calculator, especially if you don't put the negatives in the parentheses, won't use the exponents correctly. But we're 6 exponents out, divided by 1 minus negative 5. So think about what's going to happen here. We're going to get 6 times 1 minus negative 5 to the 6th power over 6. And I bet those 6's cancel. And that's going to leave us with just 1 minus negative 5 raised to the 6th power. Which looks like it is a negative 15,624. So that's how we would finish this one off. And I think that finishes off this lesson. Hopefully it was helpful in seeing how you do some of these problems. The first assignment on sequences and series is going to be from the textbook, 16 problems on page 749, a mixture of some arithmetics and some geometrics. I think the last section is the geometric ones, and they're always a little bit trickier. So make sure you use your notes and your examples to help you, and we will be available for you tomorrow for questions, and then we're going to give you another night of practice on this. The next page of your book, which is going to be page 16, workbook section 2, page 16, is going to give you a whole bunch more practice on these problems. In the meantime, though, here are some answers for the first 6 problems from the textbook. I know the textbook has the odds, but here's the evens also. Remember, you can freeze frame this and check them. And then here are the next 6, which appear to all be arithmetic problems. There's the work shown for number 12, in case you wanted to see how that broke down. Okay. And finally, here's the fun ones, the last 4, with a little bit of work shown on those. Once again, we'll be available for more questions on Wednesday. But in the meantime, good luck with your practice, and we hope that everybody is hunkering down, staying well, and your families are healthy. Take care.